Tonight, we're exploring that quiet cosmic secret, why the moon never seems to turn. We'll learn how gravity slowed its spin, how tidal forces shaped its face, and why it will always keep one side hidden from our eyes. Along the way, we'll visit the far side of the moon, explore its gentle wobble, and discover how this simple balance keeps Earth's tides, time, and tilt in harmony. If these peaceful space stories help you drift off or just quiet your thoughts, I'd love for you to subscribe and join us again. Now, take a slow breath. Let your curiosity rise like moonlight on calm water. Together, let's follow the quiet rhythm between Earth and its oldest companion. Chapter 1. The Illusion of Stillness. From your window, the moon can feel like a patient statue hung in the sky, a silent, unblinking face that never changes its position no matter how long you watch. I remember lying on my back as a kid, convinced it was keeping one steady eye on the neighborhood, like a guardian that never moved. For a long time, that's exactly what many people assumed. The moon was a static object, staring endlessly at Earth. But there's a tiny trick being played on us. The moon does rotate. It just does it on a timescale so graceful and matched to its orbit that, from our vantage point, it looks frozen. The moon turns on its axis once every 27 days, and it takes the same amount of time to travel all the way around Earth. Because those two motions are locked together, the same hemisphere of the moon is always facing us. That steady gaze we see from our window is an illusion, born from perfect timing. Think of it like two dancers in step. As the moon orbits, it also spins just enough so that the same surface constantly faces the Earth. If the moon didn't rotate, we'd see different parts of it during a full orbit. If it rotated faster, the view would shift. But because rotation and revolution match, the pattern we see never seems to change. That precise matching is called synchronous rotation, or tidal locking. Synchronous rotation didn't happen by magic. Over billions of years, gravity and friction quietly reshaped the moon's motion. Earth's gravity tugged a tiny bulge in the moon's shape, a stretch that tried to line up with our planet. As the moon spun at different speeds in the distant past, that bulge lagged behind and produced friction inside the lunar interior. That friction removed energy from the moon's rotation and eventually slowed it down until the bulge stopped shifting, leaving the moon tidally locked to Earth. It's an elegant balance. The tug-of-war calmed into a steady handshake. I like imagining that history because it turns the moon from a frozen statue into a participant in a very long, low-key conversation with Earth. Every night I look up, I'm seeing the outcome of a slow gravitational negotiation that finished long before humans ever existed. There's something comforting about that the calm face we know isn't stillness by accident, but the end of a process that shaped both bodies. Even though we always see the same general face, the familiar Maria and craters that give us the man in the moon image, the moon isn't perfectly locked in place. It has a subtle wobble called libration that lets us peek a little beyond the edges. Over time, that wobble allows observers on Earth to see about 59% of the lunar surface, not just 50. So every once in a while, if you stare long enough, you might catch a tiny shift that reveals a sliver of a landscape, usually hidden from view. There's also a human side to this illusion. For centuries, the moon's steady face fed myths and stories. We named features, drew faces on it, used it as a calendar and a symbol. When you realize that same side is no accident, it changes how those cultural images land. The moon we painted in folklore the constant companion, is literally locked to us. That's why songs about always being there, or poems about a perpetual witness, feel so apt. The moon's visible constancy has been a real, physical presence in our nights. Scientifically, calling it synchronous rotation gives us a neat word to hang on to. But part of its power is how simple and visual the idea is. Rotate once, orbit once, and the same face keeps looking this way. It's a gentle balance, not a violent constraint. The moon isn't stuck. It's chosen a motion that matches its path, and from where we stand, that matching looks like stillness. So next time you glance up and feel the moon's unblinking stare, remember the quiet choreography behind that calm look. It does spin, just not in the way you might expect. What feels like a frozen companion is actually the result of billions of years of gravitational diplomacy. That subtle, perfect sync between rotation and orbit is what astronomers call synchronous rotation, and it's the reason the moon can look so serenely motionless from your window. Chapter 2. What it means to spin. Imagine the moon as a dancer circling the Earth. Each step around the stage is one orbit, and every slow twirl is one rotation. Picture the two performers, the Earth in the center, steady and grounded, and the moon moving around it with a deliberate, elegant pace. If the moon, our dancer, turns exactly once while making a full circuit, she will always be facing her partner. That's the idea in its simplest form. The moon spins once for every orbit, so the same face is always turned toward the Earth. Put yourself in the audience. Maybe you've sat on a porch or walked down a street and looked up, thinking the moon is frozen in place, watching you like a portrait hung on the sky. That sense of stillness comes from this perfect timing. The moon is not actually stationary. It's moving across the sky every night as Earth rotates and as it makes its long trip around us. But because it rotates at the exact same rate that it orbits, its near side, the one with familiar dark seas and bright highlands, never surprises us with a brand new face. It's like watching the same dancer spin in the same direction every lap, always showing her front to one partner. Comforting, almost intimate. Try a little exercise to feel it physically. Stand in the middle of a room and imagine a friend walking slowly around you. Now tell your friend to turn once so they're facing you the entire time they make a full circle. If they only make half a turn, they'll present their profile at other points. If they spin too fast or too little, they'll briefly turn away. But if they complete exactly one turn per lap, your eye will follow familiar features the whole way. That's the moon's movement. One perfect turn per journey around Earth. Why does that produce the strange stillness we notice? Because rotation and orbit, though both motions, can cancel our intuitive sense of motion when they're locked together. On Earth, we're used to rotation making things change rapidly, day and night in 24 hours, and orbit causing slower changes like the seasons over a year. The moon's rhythm is matched so precisely that its spin hides itself. From our vantage point, the moon appears to present a fixed face while all the underlying motion keeps happening, a paradox that's almost poetic. There's a gentle twist to the story, though. If you watch carefully over many nights, you'll notice the moon does not remain perfectly frozen. It nods and rocks subtly. Those small, wobbling motions are called librations. Think of them as tiny improvisations in the dance. A shoulder shimmy here, a slight lean there, that let us peek a little beyond the edges of the moon's face. Because of libration, we can eventually see about 59% of the lunar surface over time, even though at any one moment, half of the moon is hidden. The moon's steady orientation is not absolute, but it's close enough to feel like a still portrait from below. People often ask whether this synchronous motion is unusual. It isn't unique in the universe, though it feels special when you look up. Tidal forces, the same gravitational tug that makes Earth's oceans bulge, slowly coaxed the moon into this pattern. Imagine a slow cosmic friction. The Earth's gravity pulls slightly harder on the moon's near side than on its far side, creating tiny bulges. Over millions of years, those tidal interactions acted like a brake, dissipating energy and nudging the moon's rotation into lockstep with its orbit. The result is stability and predictability. Two partners, so used to each other's steps, they move as one. Making this personal, think about the idea of always facing one person as a metaphor for familiarity. When you gaze at the moon, you're seeing the same face that countless people have admired for millennia. Our grandparents, poets, and explorers all looked up and recognized those seas and craters. There's comfort in that continuity, like a friend who shows up every time you look out the window. At the same time, the moon's hidden backside whispers of mystery. Knowing that more than half of our nearest neighbor remained unseen by human eyes, until relatively recently, adds a human-scale excitement to the science. Even something so close had secrets. That dance also shapes our everyday life in subtle ways. The moon's gravitational pull affects tides, which in turn influence coastlines and ecosystems. The predictability of its motion makes it a reliable clock for ancient and modern timekeepers. Sailors, farmers, and poets have all found ways to use the moon's steadiness. And for astronauts, the synchronous spin is a practical consideration. From lunar orbit or the surface, what you can see and where you can land depends on which face is toward you. So when you think about the moon spinning, don't picture a distant rock whirling randomly in space. Picture a deliberate dancer, trained by gravity, choosing to turn once as she circles, always facing her partner. That synchronized motion creates the beautiful paradox we see from Earth, a world that is constantly moving, and yet, to our eyes, almost perfectly still. It's a cosmic waltz of perfect timing, and next time you glimpse the moon, you're watching one of the universe's oldest choreographies in motion. Chapter 3. The Tidal Locking Secret. The secret lies in gravity's patience. Imagine the moon as a proud, spinning dancer on a vast stage. Long ago, she pirouetted freely, turning her face to the stars and then to us, showing different features with every revolution. But Earth was an insistent partner. Its gravity didn't yank or shout. It tugged, gently but relentlessly, on the side of the moon closest to us. That tiny, persistent pull is where the story begins. Think of a round ball of soft dough. If you squeeze one side, a bulge forms. That's what Earth's gravity did to the moon's rocky body. It raised slight tidal bulges toward and away from Earth. Those bulges weren't dramatic. The moon is solid and stiff compared to an ocean, but even a small distortion matters when it happens over millions of years. As the moon kept spinning, those bulges tried to rotate with it. Inside the lunar interior, this movement created friction. Rocks deforming and flexing dissipate energy as heat, and that gradual loss of rotational energy is what slowed the moon down. If you've ever tried to spin a heavy top in syrup instead of air, you know how a resisting medium eats away at motion. The moon's bulges provided that resistance. Every tiny flex, every grain of rock shifting imperceptibly, robbed the rotation of a little momentum. The result wasn't a dramatic stop, but a steady braking, a cosmic patient deceleration. Over vast spans of time, that slowdown continued until the moon's rotation period matched its orbital period around Earth. At that point, the bulges no longer dragged across the surface. They stayed aligned, the frictional torque vanished, and rotation and orbit settled into a synchronized rhythm. Now, try to picture what that synchronization feels like in human terms. Imagine you and a friend walking around a campfire, linked at the elbow, matching each other's pace so one face is always turned toward the other. It's not that one of you stops moving. You both keep walking around the circle, but your relationship changes. The moon didn't stop orbiting Earth. It simply locked into a steady face-to-face routine. One hemisphere became our constant companion. The other was left to stare forever at the darker reaches of space. That familiar near side we see every night tells the story of that long, intimate interaction. This process, called tidal locking, is gravity's way of bringing order out of motion, calm out of chaos. It's not instantaneous. If you could replay the last 4 billion years and fast forward, you'd see the moon's spin gradually ebbing, tidal bulges forming and fading, and the slow transfer of angular momentum sculpting a stable configuration. That slowness is part of the beauty. There's something almost comforting about the idea that simple physical laws, given enough time, convert jitter and randomness into quiet regularity. You can find echoes of tidal locking closer to home. Many moons in the solar system show the same behavior. It's the cosmic equivalent of settling into a comfortable pace with someone you orbit around day after day. In some systems, the effect is mutual. When bodies are similar in size, they can lock to one another, forever showing the same faces, as Pluto and Charon do. And sometimes you get partial locking. Mercury, for instance, ended up in a 3.2 resonance with the Sun, rotating 3 times for every 2 orbits. The universe experiments with different outcomes, but the underlying tool is the same. Gravitational tugs, creating deformations and friction that nudge systems towards stable configurations. There's also a human-scale contrast that makes tidal locking relatable. Think about the way your wrists get tired when you hold a heavy tray outstretched. At first, you can keep moving it this way and that, but sheer repetition wears you down, and eventually you adjust your grip or posture to something easier to maintain. Gravity, over eons, forced the moon to adjust its posture. It found the easiest way to maintain its relationship with Earth. Always the same face forward, a detail worth picturing. The bulges weren't perfect, centered lumps of rock. As the moon turned, the bulge closest to Earth wanted to point straight at our planet. But when the moon was spinning a little faster, that bulge would be slightly out of place, lagging behind the direct line to Earth. That slight misalignment created a torque, a gentle twisting force that opposed the rotation. The physics is elegant and almost modest in its simplicity. Misaligned mass, gravitational pull, internal friction. Repeat that over and over, and you get synchronization. For those of us who look up and feel a small private connection to the moon, this makes the familiar face even more personal. Every crater, mare, and wrinkle of that face is the visible outcome of an ancient conversation between two bodies, a slow negotiation hammered out by tugging and flexing. When you stare at the moon tonight, you're seeing the end state of a relationship that had to go through discomfort and change to reach comfort and continuity. That relationship isn't frozen forever. The Earth-Moon system still evolves. Because of tidal interactions with Earth's oceans, the moon is gradually moving away from us, inching farther by about a few centimeters each year. As it retreats, the dynamics change subtly. The orbital period lengthens, and over unimaginably long time scales the balance could shift again. But for now, tidal locking has given us a stable, dependable companion, a moon that reliably shows us the same face, a reminder that even the immense forces of gravity prefer the slow, steady work of order-making over flashy, sudden acts. So the next time you see the moon hanging low and full, or thin as a sliver, remember that you're looking at the result of patient physics. It's not fate or magic making that face familiar. It's gravity's persistence. Tidal locking turned a once-free spinner into a steady partner, and in the process it taught us a quiet lesson. Given enough time and a gentle but unrelenting nudge, chaos gives way to rhythm. Chapter 4. Billions of Years of Balance. Think about the moon, not as a frozen statue in the sky, but as an old, patient partner in a slow dance. That dance didn't find its rhythm in a single heartbeat. It took hundreds of millions of years, an almost unfathomable stretch of time, for the moon's spin to be tamed by Earth's gravity. Back then, the newborn moon was rotating more quickly, wobbling and reorienting as both bodies exchanged energy. Over time, tiny bulges of rock and tidal friction acted like invisible brakes. Those small nudges, repeated endlessly, robbed the moon of extra spin until one face settled permanently toward us. That's tidal locking, a long, quiet settling into harmony. Put it on a human scale. Imagine pushing a child on a giant swing. At first, their movement is wild and fast. Then, with the right timing and pull, the swing smooths into a steady rhythm. But for the moon, the smoothing took far longer than any human lifetime. For us, the result is immediate and familiar. The same lunar face always turned toward Earth, those familiar craters becoming a constant companion over the millennia. Once that equilibrium formed, the Earth-Moon system entered a stable chapter, not frozen, still moving, still exchanging, but steady in a way that allowed life to adapt and cultures to record time. Gravity became the invisible thread between two worlds, pulling and responding. Even now, though our eyes see a placid moon and calm tides, the tug is constant. It reaches across space and time, tugging gently at the oceans, shaping coastlines, and setting rhythms that creatures and people have learned to read. Go to a beach on a quiet evening and watch the water. You'll see the moon's influence in a way that feels intimate. The tide doesn't surge because the moon is blasting waves at us. It bulges the ocean toward and away from Earth. That bulge moves as the Earth turns, and where you stand, water rises and falls. Those changes are predictable, patient, and life-shaping. Intertidal zones, the muddy flats and rocky ledges between high and low tide, are testaments to that predictability. Organisms there live by schedules set by lunar gravity, crabs timing their feeding, barnacles opening and closing at the right moment, tiny creatures hiding until the water returns. If you've ever walked those flats, fingers chilled by seawater, you've participated in a rhythm that goes back billions of years. Tides are more than coastal spectacles. They influence entire ecosystems. Coral spawning, for example, often pairs with lunar cycles. Millions of coral polyps release sperm and eggs in near-perfect synchrony under certain moon phases. Some fish and invertebrates time migrations and breeding to tidal rhythms, so offspring are carried to favorable nursery grounds. Even wetlands and estuaries, which act as nurseries for fish and buffers for storms, depend on tidal flushing to bring nutrients and carry waste. The moon's pull is a gentle metronome, and life has learned to dance to it. Humans are woven into that pattern too. Our earliest calendars and mythologies were lunar. People watched the changing face of the moon and used it to mark months, to plan planting, to choose times for travel or ritual. The phases, new, crescent, full, became a way to measure time long before mechanical clocks. Walk into any traditional fishing village and you'll hear older generations speak of spring tides and neap tides like weather forecasters. Those are practical, lived pieces of knowledge passed down because the lunar rhythm affects when nets are hauled, when boats can pass safely, when shellfish beds are exposed. Even the Earth itself is changed by this gravitational conversation. The same forces that lock the moon's rotation also steal a tiny amount of Earth's spin energy, slowing our planet's rotation very slightly over geologic time. Days lengthen by a sliver, not noticeable in a lifetime, but measurable across epochs. There's also an exchange of distance. The moon is moving away from us at a pace so slow you'd barely notice over a human career, a few centimeters a year, but over eons, it's meaningful. That gradual drift is a reminder that balance in the cosmos is not a static perfection. It's dynamic, measured in epochs, not minutes. That dynamic balance has had consequences that shaped the conditions for life on Earth. The moon's gravity stabilizes Earth's axial tilt, reducing extreme swings in climate that could otherwise have made long-term complex ecosystems more difficult to sustain. In a way, the moon acts like a cosmic shock absorber, keeping our seasons and climate within ranges that allowed life to find steady footing. Thinking about that makes the moon feel less like distant scenery and more like an essential part of Earth's habitability. There's also something quietly poetic in the way the moon marks time. Look up any clear night, and you can read the month in the phase of the moon. From new to full and back, those phases are the pulse of nights and months. Sailors and farmers, lovers and poets, all of them have used that pulse as a guide. For many, watching the moon wax and wane offers a rhythm to match our own internal cycles. Sleep, work, reflection. In small personal ways, the moon's slow heartbeat synchronizes with our daily lives. It's easy to think of these processes as purely mechanical, but I like to imagine them as a long conversation between two bodies. Billions of years of small adjustments, compromises, and steadied forces have produced a relationship that feels natural to us. When you set a cup down on a table or drift off to sleep under moonlight, that calm is partly courtesy of an ancient gravitational pact. The tug you can't see has helped shape shorelines, breeding cycles, calendars, and even the length of your day. So next time you notice the moon, whether it's a silver sliver hanging over a city skyline or a big round disk over a quiet sea, take a moment to feel your place in that slow alignment. You're witnessing the lingering effects of a process that took far longer than human history to complete, and yet its gentle pull touches the smallest routines of life. That balance between Earth and Moon isn't finished. It's a continuing story, written slowly in tides, in drift, and in the quiet turning of our skies. Chapter 5. The Far Side. Not the dark side. When people say the dark side of the moon, it has a nice ring to it, mysterious, a little ominous. But it's also wrong. Imagine calling one side of a clock permanently the dark side, just because you can't see it from where you're sitting. The moon is much the same. Every part of it gets sunlight, just not all at the same time. What we call the far side is simply the half that always faces away from Earth. It isn't cursed or forever twilight. It's just been shy. Think about that for a second. If you've ever turned to face a friend and then kept your face toward them, gradually your back becomes the far side from anyone behind you. The moon was put in that position by gravity, the same patient tug that keeps it on a steady path around our planet. Over billions of years, Earth's gravity nudged the moon's rotation until it matched its orbital period, a state we call tidal locking. The result is the moon showing us one face forever. That's not destiny or drama. It's the quiet math of celestial motion. Because of that lock, every lunar day lasts about 29.5 Earth days. For roughly 2 weeks, a spot on the moon basks in sunlight. For about 2 weeks after, it sits in night. So, the dark side is a myth. Each hemisphere gets its share of dawns and dusks, slow, long, and spectacular. Imagine a sunrise that stretches over several Earth days, soft light crawling across craters and throwing long, otherworldly shadows. If you could stand there, you'd see the sun rise like a faint coin, and the light would stretch, revealing textures and scars no quick sunrise on Earth could. For billions of years, though, no human had ever seen the far side. Our ancestors stared up at the moon and invented stories about its face. The man in the moon, harvest calendars, lovers' glances. Nobody saw the other half. It wasn't until the space age, in the late 1950s and into the 1960s, that machines finally peeked over the lunar shoulder and sent back the first photographs. Those grainy images were a revelation. The other side looked different, stranger, where the near side has broad, dark plains called Maria. The word means seas in Latin, because they looked like oceans to early astronomers. The far side is a highland world. It's more rugged, punched full of craters and scarred by a history of impacts. Imagine a face that's been more weathered, more pockmarked, with fewer smooth plains to soothe the eye. The highlands are brighter, rockier, and in many places, more chaotic. It's easy to think of it as uglier, but that's a mistake. Its beauty is raw and honest, the kind you admire in an old, knotted tree rather than a manicured garden. Why the difference? It comes down to the moon's geology and a bit of luck. The near side's crust is thinner in places, which let ancient volcanic flows fill basins and create those dark maria. The far side's crust is thicker, so when massive impacts punched holes, hot molten rock didn't as readily flood the surface to form those large dark plains. So instead of broad seas of basalt, we get a landscape that's a time capsule, a preserved record of billions of years of collisions and cosmic debris. There's something quietly poetic about that. The far side is a memory bank. Each crater, each overlapping basin is a line in a story that predates life on Earth. Scientists love it for that reason. The far side preserves ancient terrain that hasn't been remodeled by later volcanic activity. It lets researchers piece together a cleaner chronology of impacts and early solar system events. If you want to understand how the inner solar system evolved, the far side is one of the best archives we have. And for people like us, curious observers on a small blue planet, the far side is relatable because it feels like a private place. Picture standing on that surface. There's no Earth in the sky. Our home, which for us is always present, would be absent. That absence changes how the landscape feels. No familiar blue marble to anchor you, no thermostatic presence of a parent planet. Just the moon, its horizons, and a sky full of stars. Many astronauts and mission planners describe that as eerie and beautiful. It's a reminder that context matters. The same place can look very different when the frame of reference changes. That no Earth perspective also makes the far side scientifically useful in another way. Earth is loud. Between radio broadcasts, satellites, and all our electronic chatter, near-Earth space is a noisy place at radio frequencies. The far side, shielded from that noise, is the quietest radio environment near Earth. Astronomers dream of placing low-frequency radio telescopes there to listen to signals that get drowned out by our planet. We could probe the early universe, detect faint cosmic whispers, and listen to events we can't hear from Earth. The far side is like a natural radio sanctuary. It's also the scene of a modern milestone in our relationship with the moon. In 2019, China's Chang'e 4 made the first ever soft landing on the lunar far side, sending a rover called U-22 to explore the region. That mission gave us close-up views of terrain we'd only seen from orbit, revealing surprising textures, rock fragments, and a new level of complexity. It was history in a quiet place, people on Earth cheering as a robotic emissary rolled across a part of the moon no living human had stood on. That combination of mystery and accessibility is what makes the far side so compelling to ordinary people. It's not a Hollywood dark side full of monsters. It's a real landscape with a story we can begin to read. It's also a little like meeting someone who's always been shy. For years we shaped myths about them, then finally got a photo and realized how much subtle detail we'd missed. Once we begin to pay attention, we see that their life, their scars, their quiet, tells us more about who they are than any rumor could. I remember the first time I looked at a photograph of the far side and felt that shift. The moon went from a familiar face to a full character with depth and hidden chapters. It stopped being symbolic and started being tangible. That's the power of changing perspective. It's a lesson that applies beyond astronomy. Sometimes we project stories onto what we can't see. When the veil lifts, the truth is often more interesting than the rumor. So the next time you hear someone talk about the dark side of the moon, you can smile and picture slow sunrises and rock-strewn highlands. Picture an atlas page full of craters, an archive of impacts. and a radio-quiet sky waiting for our instruments. Picture a place that's been hidden from our eyes for as long as our species has existed, now gradually being unveiled by machines and, someday, by people. It's not the dark side, it's the far side, and its light is just delayed. And beyond the science, there's a human truth in that delayed light. The far side reminds us that there's always more to discover, parts of our world and ourselves that remain unseen until we build new tools, ask better questions, or simply change our viewpoint. The moon's patient gravity keeps one face turned away from us, but gravity also keeps everything in motion, nudging us forward. We're finally learning to look where we've never looked before, and the far side is answering back with a landscape both ancient and alive with possibility. Visual cue: slow pan across far side terrain, long shadows stretching over crater rims, cut to archival images from early lunar probes, then to footage of Chang'e 4 and Yutu-2. Close with a lingering shot of the moon without Earth in frame. A quiet, powerful reminder that mystery can be beautiful, not sinister. Chapter 6. The moon's gentle wobble. Even though the moon is tidally locked, always showing roughly the same face to Earth, it isn't frozen in place. Think of it more like a dancer who, while keeping her face toward the audience, shifts her shoulders and tilts her head. That subtle shift is called libration, and it's the reason we don't just see a perfect half of the moon. Over time, that gentle wobble lets us peek around the edges. Instead of 50% of the lunar surface, we can see about 59% from Earth. Let's make that feel real. Have you ever watched the moon for a week or two and noticed that some dark patches and craters near the edge seem to creep into view, then slip away? That's libration at work, a slow, rhythmic breathing. From one night to the next, a feature near the limb might be partly hidden. A few nights later, it'll be more exposed. If you keep a simple sketchbook or take photos across a month, you'll actually trace those tiny shifts and watch the far side yield fleeting glimpses of its rim. There are 3 main flavors of libration, and each has an easy image to hold in your head. Longitudinal libration comes from the moon's elliptical orbit. The moon's rotation on its axis is almost perfectly synchronized with its orbital period. But because the orbit is slightly stretched into an ellipse, the moon speeds up and slows down a bit along its path. Its spin doesn't speed up or slow down in perfect step, so from Earth we see the moon nod slightly east and west, like a clock face that oscillates by about 7 to 8 degrees. That's enough to reveal a sliver beyond the average edge on alternating sides. Latitudinal libration is a north-south nod caused by the tilt of the moon's rotational axis relative to its orbital plane. Imagine the moon tipping its poles toward and away from us over the course of its orbit. That tilt swings features near the lunar poles up into view and then away again, with an amplitude of roughly 6 to 7 degrees. Diurnal libration is the smallest and most familiar on a human scale. It comes from where you're standing on Earth. Because observers are seeing the moon from slightly different angles as Earth turns, the moon appears to shift up to about 1 degree over the course of a night. It's a tiny effect, but for careful observers using binoculars or telescopes, it's measurable. Combined, these motions add up. The moon doesn't literally rotate back and forth like a pendulum. Instead, the combination of longitudinal, latitudinal, and diurnal librations produces a complex but still gentle wobble that repeats with the lunar month. The result is a slow reveal. Features that sit just over the horizon of the average face come into view, then fade, like a shy friend leaning to say hello. Why does this matter, besides being a delightful trick of celestial mechanics? For one thing, it's how early astronomers and map makers squeezed more information out of telescopes. Before we had spacecraft that could photograph the far side directly, careful observers relied on libration to get partial looks at regions beyond the average limb. Those brief glimpses let them sketch and name features that would otherwise have been hidden. Even today, libration matters for lunar photography. If you want the best possible view of a particular crater or mare near the edge, you plan observations to coincide with favorable libration. It also affects how features appear. Craters and mountain ranges near the limb get foreshortened. They look squashed or stretched, and libration changes that perspective over time. For amateur observers, that means the moon can feel like a living landscape whose shapes subtly warp across nights. One night, a wrinkle of highland terrain might look like a faint scallop. A week later, the same region may be revealed more fully, showing its true form. That shifting gives the moon a dynamic character that's easy to miss if you only glance up for a single night. There's a human element to this too. Imagine lying on your back on a cool night, the moon bright and steady above you. You don't need an expensive telescope to notice libration. A pair of binoculars and a calendar of dates will do. Pick a feature near the limb, maybe a distinct dark patch or a noticeable bright crater, and follow it through a few lunations. You'll begin to recognize the pattern in the sway, and it becomes a private rhythm between you and the sky. Astronomers across centuries have felt that same quiet fascination. The moon feels familiar and mysterious at once, because it never quite shows all of itself at once. Libration also explains some of those small mysteries people notice when they compare lunar photos from different months. Two pictures taken of the same part of the moon can look slightly different, not just because of lighting, but because the viewing angle has changed. Shadows cast by crater walls and mountain ridges react dramatically to tiny shifts in illumination, and when libration changes the angle of view, those shadows and outlines change too. That's why a lunar atlas will often show slightly different silhouettes of limb features. They're literally being revealed from different angles. From a scientific point of view, those glimpses matter for mapping and planning. When missions were being planned, mission designers accounted for libration to ensure landing sites and communications lines would behave as expected. Even now, when orbiters map the far side comprehensively, libration is still part of the story for telescopic observations and for amateur imaging projects that contribute to long-term monitoring. There's also something poetic about the scale of these motions. The numbers, a few degrees in either direction, sound small, but when you consider the moon's diameter of 3,474 kilometers, even a few degrees of tilt expose an enormous stretch of terrain along the limb. It's like watching someone turn slightly on a stage, and suddenly we glimpse a whole new slice of the set. Over time, that slice accumulates, and our cumulative view of the moon grows from a flat, static disk to a more rounded, three-dimensional picture. How to watch libration for yourself? Pick a predictable schedule and stick with it. The basic cycle ties to the moon's sidereal month of about 27.3 days. That's the time it takes to return to the same place relative to the stars. So over the course of a month, you'll see the full range of longitudinal and latitudinal librations. use a small telescope or binoculars to track limb features across multiple nights, and pay attention to the moon's position against the background stars. That helps you notice the subtle east-west swings. There are also simple online calculators and lunar ephemeris sites that list libration angles for any given date. Those let you plan an evening when a particular limb region will be tipped toward Earth. Finally, don't underestimate the delight of the metaphor. Describing the moon as breathing isn't just poetic license, it's a useful image. The slow inhale and exhale of libration makes the lunar surface feel intimate and ever-changing. It invites repeated looks, invites curiosity. What lies over that rim tonight that wasn't there last month? That sense of small, patient revelation is part of why the moon has always captured our attention. Give it a little time and a bit of patience, and you'll see the moon do what it's been doing for eons. Reveal, conceal, and reveal again, one soft wobble at a time. Chapter 7. Earth's Pull and the Moon's Loyalty. Picture two dancers on a dark stage, one large and steady, the other smaller and circling close. Gravity is the invisible hand that keeps them together, a slow, elegant choreography that's been repeating for billions of years. That smaller partner, our moon, always turns the same face toward Earth. It's not a coincidence, it's the result of tidal locking, where the moon's rotation period matched its orbital period long ago. So while Earth spins beneath it every 24 hours, the moon completes one rotation in roughly 27.3 days, always presenting the same familiar face we've come to know. That steady orientation feels personal when you think about it. If you grew up lying on your back and tracing the craters with your finger, or taking late-night walks lit by soft lunar glow, you probably didn't realize you were looking at a silent promise. The moon will always look back. That constancy is reassuring in a way, like a friend who never misses your call. But it's more than sentimental. It has huge practical effects on life here. First, the tug of the moon creates tides. The same gravity that keeps the moon in orbit pulls on Earth's oceans, lifting bulges of water toward and away from the satellite. Tides are the visible heartbeat of that gravitational relationship. For coastal communities, tides shape daily routines. Fishermen plan trips around them. Surfers read them like a second language, and entire ecosystems, marshes, estuaries, intertidal zones, depend on those rhythmic in and out flows. Imagine trying to explain low tide to someone who has grown up on a planet where shorelines never change. It's hard to overstate how much of human culture and natural life has adapted to this lunar cadence. But the moon's influence goes deeper than tides. It acts as a stabilizer for Earth's axial tilt, the angle that Earth's spin axis makes with the plane of its orbit around the Sun. That tilt, around 23.4 degrees now, is what gives us seasons. Tilt the axis a little more, and summers at one pole would be scorching while winters plunge into deep cold. Tilt it less, and seasonal contrast fades. Imagine a world where one year the tilt is comfortable and familiar, and the next it swings wildly. Your calendar would stop being a reliable guide for when to plant crops or prepare for storms. Here's the critical role the moon plays. Its gravitational pull exerts a steady torque on Earth that keeps our tilt from wandering chaotically. Without that stabilizing effect, simulations suggest Earth's tilt could vary much more over geological timescales, possibly swinging by tens of degrees. That would mean unpredictable extreme climate shifts over thousands or millions of years. For life as we know it, ecosystems, migration patterns, agriculture, even human cycles of planning, predictability matters. Think about how farmers use seasonal norms to plant, how migratory birds follow the same cues year to year, how we schedule holidays and school calendars around seasons. If the ground rules kept changing, those routines would be upended. There's also a more intimate physical consequence. The moon's tug has gradually slowed Earth's rotation. Billions of years ago, a day was much shorter. Through tidal friction, energy is transferred from Earth's spin to the moon's orbit, nudging the moon slightly farther away at a rate we can measure today, about 3.8 centimeters per year. The lengthening of days over geological time gave life steadier cycles to adapt to. Many biological rhythms are tied to day-night and seasonal cycles that evolved under the influence of this very interaction. Picture your own circadian rhythm, that sleepy feeling after sunset, or alertness with morning light, all shaped by a planet that spins at a relatively stable pace. Now imagine the alternate, no moon, or a much smaller one. The Earth would be more like an unsteady top, wobbling under the gravitational pulls of other planets and the Sun. Without the moon's consistent torque, models show Earth's obliquity could vary dramatically. Some scenarios envision swings that push the axis toward 45 degrees or more. That's not just a bit more snow or a slightly longer summer. It's rearranging climate zones, shifting deserts north or south, altering where ice sheets form and how ocean currents circulate. The long-term consequences could include repeated, extreme glaciations or prolonged, intensified warmth in some regions, each lasting millennia. Enormous stress for ecosystems trying to keep up. You don't have to be a scientist to feel the implications personally. Think about the simple pleasures and certainties you rely on. Seasonal produce showing up in markets, knowing when to pull out winter coats, planning a summer vacation for guaranteed beach weather, or counting on migration patterns for bird watching. Those are woven into daily life. A planet with a wildly varying tilt would make seasons unreliable, and whole cultural rhythms, festivals tied to harvests, construction seasons, the school year, would face unprecedented instability over time. There's a poetic side to it too. The moon's loyalty is like a quiet guardian, patient and persistent. It steadies Earth while allowing enough variability to make the world interesting. Seasons that bring color and contrast, night and day that structure sleep and work, tides that sculpt coastlines and nourish unique habitats. Its influence is subtle. Most days we take it for granted because its effects are steady, not flashy. But that steadiness has been essential for life to diversify and flourish in relatively predictable ways. Visualize for a moment standing on a beach as the tide pulls away, revealing creatures that are used to that rhythm: crabs, starfish, and shorebirds moving with practiced timing. Think about farmers checking the long-term forecast and trusting the seasons to come. Or remember a childhood memory of watching a full moon and feeling reassured. Those small, everyday moments are threads in the larger tapestry woven by the Earth-Moon gravitational relationship. As we watch the moon continue its slow dance, receding a few centimeters each year, holding its face to ours, influencing oceans and tilt, It's worth appreciating how that cosmic companionship made our world the one we know. The moon's loyalty isn't just romantic. It's practical, climatic, biological, and cultural. It's the quiet reason that, for now, our seasons are reliable and our calendars make sense, and why many forms of life could evolve the timed cycles they depend on. Transitioning from that steady partnership, let's next look at how the moon's rhythms show up in the lives of other species, and how organisms have tuned themselves to lunar cycles in ways you might not expect. Chapter 8. Other Locked Worlds. The moon isn't alone in its stillness. Most large moons in the solar system have come to the same quiet arrangement, patiently showing one face to their parent for millions or billions of years. If you picture the moon eternally gazing at Earth, that image plays out again and again, but with very different personalities. Take Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto. They're all tidally locked to the giant, each keeping the same hemisphere pointed at Jupiter as they orbit. That sounds calm, almost comforting, but locked doesn't mean dead. In fact, tidal locking is a kind of steady pressure, and pressure can create heat, motion, and surprising drama. Io, the innermost Galilean moon, is a perfect example. Because its orbit is slightly eccentric and it's constantly tugged by both Jupiter and its neighboring moons, Io gets flexed like a rubber ball in a hand. That flexing generates enormous internal friction and cooks the moon from the inside out. The result? Hundreds of active volcanoes, lava fountains, and a landscape that's being remade before our eyes. A locked moon that's anything but still. Europa gives us the opposite, quieter promise, locked in the same gravitational handshake. Its icy shell hides the possibility of a global ocean beneath. The tidal tugging isn't turning the surface into molten rock, but it's enough to keep water warm under ice, to sustain a vast, dark ocean that could, in some ways, be more like a deep, familiar ocean here on Earth than the airless deserts we often imagine on other worlds. Thinking about a locked world with liquid seas beneath a frozen lid makes you imagine strange, slow ecosystems, places where life, if it exists, has adapted to stillness and constant gentle motion. Ganymede, the largest moon in the solar system, is locked too and brings another twist. It's big enough to have its own magnetic field. Even in a synchronous spin, internal oceans, layered structures, and subtle movements can generate magnetic signatures. And Callisto, the most battered and ancient of the four, is a record keeper. Its heavily cratered surface reads like a history book of the early solar system, preserved in a locked pose. Then there's Pluto and Charon, which raise the idea of locked to a romantic extreme. They're mutually, tidally locked. That means Charon always shows the same face to Pluto, and Pluto always shows the same face to Charon. Imagine two dancers frozen in mid-conversation, never turning away. For someone standing on certain regions of Pluto, Charon would never leave the sky. For others, it would hang permanently at the horizon. It's intimate and a little eerie, a two-body system that settled into a mutual embrace. Why does this happen so often? It's just physics, but it's oddly relatable if you think about it in human terms. Gravity creates tiny bulges and torques. Over time, those torques sap rotational energy and leave the bodies in a minimum energy state. one face forever fronting its companion. The process can take millions to billions of years depending on mass, distance, and how squishy the bodies are. The end result is balance achieved through stillness. But the story doesn't stop at balance. Tidal locking changes everything about a world: its geology, climate, potential for life, even the way it would feel to stand on its surface. Locked worlds can be volcanically violent or serenely oceanic. They can hold magnetic fields, host ancient surfaces, or hide warm oceans under ice. The common outcome, a spinning body slowed and synchronized, is simple, but the consequences are rich and wildly different. And beyond our neighborhood, this pattern repeats itself. Around other stars, planets too can become tidally locked, particularly those close to faint, small stars called red dwarfs. If a planet sits tightly in its star's habitable zone, one side might bake in constant daylight while the other freezes in perpetual night. Yet even there, the dance can create habitable niches, the twilight ring between day and night, atmospheric currents transporting heat, and maybe oceans that redistribute energy. The cosmos seems to favor this solution of stillness time and again as a natural endpoint of gravitational choreography. On a personal level, there's something comforting about that steadying force. We like to think of movement as life, but these moons show that rest, the kind enforced by long, patient physics, can also be creative. Locked doesn't mean lifeless. Locking can be a crucible. It can be the slow sculptor that drives volcanoes, maintains hidden seas, or preserves ancient scars. It's a reminder that stability and change can coexist. A world can be fixed in orientation, yet wild inside. So next time you look up at our moon and feel that quiet, familiar face, remember it's part of a larger gallery of locked worlds. Some are boiling, some are glacial, some are magnetic, and some keep one another company forever. Across the cosmos, tidal locking is a common outcome of time, gravity, and motion, an elegant, patient equilibrium that turns dynamism into a new kind of stillness. That idea, balance achieved through stillness, feels almost human, a cosmic mirror for the ways we find steadiness in the things that shape us. Chapter 9. If the moon spun freely. But imagine for a moment the moon was not frozen in that polite, unchanging pose. Imagine it spun freely, like any other rocky body in space, turning on its axis as it orbits us. From our backyard chairs, from the roof of a car on a summer night, we would no longer be greeted by that same familiar face. Every night, the moon would show us a different patch of scarred crust, a new arrangement of Maria and Highlands sliding slowly across its disk. The idea is oddly intimate. The moon would become less a portrait you hang on the wall and more a conversation partner who keeps revealing a new expression. Think about how that would feel. Right now, there's comfort in consistency. We know where the sea of tranquility is. We know the crooked line of Imbrium. Children learn to pick out the dark man in the moon. These aren't just landmarks on a rock. They're part of how we anchor nights, how poets and late-night lovers find a common reference point. If the moon rotated freely, those anchors would be moving. A face you recognized last week could be replaced by a stranger tonight. It would make moon gazing feel like flipping through a slow, celestial gallery instead of standing before a single, trusted painting. Astronomically, the change would be obvious. Right now, the moon is tidally locked. One rotation on its axis matches one orbit around Earth, so the same hemisphere always points our way. If it didn't lock, the moon's rotation would mean that features on its surface would sweep from left to right or right to left across the lunar disk as seen from Earth. Phases, the crescents, quarters, and fulls, would still occur because those depend on the geometry of Sun, Earth, and Moon, not on the moon's spin. But the face you see during each phase would no longer be predictable in the everyday sense. You'd still get full moons and new moons, but each full moon might wear a different mask. That shifting mask would change more than just our sky charts. Consider light. The moon is not uniformly bright. Dark Maria and bright Highlands reflect sunlight differently. As the moon rotates, the pattern of bright and dark regions crossing the crescent would change the quality of moonlight from night to night. For people who pay attention to subtleties, photographers, wildlife researchers, fishermen, that variability would matter. Animals that cue behavior to the amount or pattern of moonlight might find their signals scrambled. Moths and nocturnal pollinators that rely on consistent lunar illumination could be affected. Think of tidal marsh animals that time feeding or breeding with moonlight and tides. Suddenly their celestial clock would have a changing face to read. And then there are the tides, a subject that anchors the moon's influence into something tactile. The basic tidal rhythm, 2 high tides and 2 low tides most days at many coastal points, is shaped by the gravitational pull of the moon across the spinning Earth. The moon's near side pulls a little harder than its far side, stretching the oceans into tidal bulges. The fact that the same hemisphere of the moon faces Earth now is part of the long-term dance of gravitational forces between the two bodies. If the moon spun freely, that dance would be less choreographed. In practical terms, what would that mean for our tides? The immediate daily pattern of high and low tides would still be governed by the moon's position in the sky, not its rotation. So fishermen and surfers wouldn't suddenly find the sea doing backflips every day. But over long stretches of time, the way Earth and Moon exchange angular momentum would change. Right now, tidal friction, the pull of the ocean against the spinning Earth, slows Earth's rotation ever so slightly while flinging angular momentum outward and nudging the moon into a slightly higher orbit. That's why the moon is slowly receding from us, at a snail's pace. Tidal locking is a manifestation of that same energy exchange. Once two bodies are tidally locked to each other, that handshake of gravity becomes steady and predictable. A freely spinning moon would interrupt that steady handshake. The torques that line up the bulges and then move energy between Earth's rotation and the moon's orbit would be distributed differently. Over geologic time, this could mean a weakening of the stable gravitational coupling we've gotten used to, a slower, less predictable transfer of energy, which could affect how quickly the moon moves away, how Earth's rotation slows, and even the long-term stability of the lunar orbit. The specifics are complex and stretch across millions of years, but the takeaway is simple. Our gravitational relationship with the moon wouldn't be as fixed as it is now. It would be more like two dancers who sometimes step out of sync and then try to find each other again. That slow shift would echo through life on Earth in subtle ways. Human culture, for one, is full of rituals keyed to a moon that behaves predictably. Calendars, folklore, navigation techniques. Many traditions assume a moon you can count on to appear in a familiar place in the sky. Sailors used the moon's position for navigation. Farmers planned activities around phases. Poets used the moon as a steady confidant. If the moon kept changing its face, cultural references would have to become more flexible. Maybe we'd develop a new kind of moon spotting etiquette, crowdsourcing a nightly map of which Maria were showing. Maybe star charts and apps would adapt, tagging not just phase but which lunar features were visible that night. There's also a psychological component. The moon's fixed face gives nights a kind of punctuation, a reliable companion on walks and late drives. People talk about seeing the moon and feeling as if a friend has joined them. The same expression returning again and again, a familiar glow. That predictability underpins a lot of small personal rituals. Stepping outside to check if the moon is full before an important decision. Waking up to an early morning crescent and feeling the world is in order. A moon that showed a surprise face every evening might make nights feel less anchored. For some, that would be thrilling. For others, unsettling. And then there's the purely aesthetic change. A moon that rotates freely would make the night sky feel more dynamic. Urban dwellers who rarely look up might catch themselves pausing more often, trying to identify a new set of shadows and planes. Amateur astronomers would suddenly have fresh targets, new angles on familiar craters, different lighting revealing hidden ridges. People would swap photos. Look at Mare Serenitatis tonight. It's on the left. It would add a layer of novelty to stargazing and maybe even bring more people outdoors to witness the moon's changing moods. But novelty comes with cost. Habits and species evolved around a rhythm we didn't create but have relied on. Coral spawning, certain bird migrations, and human sleep patterns are all at least partly influenced by lunar cycles. A moon that changes its appearance nightly wouldn't necessarily change the gravitational timing of tides in the short term, but the subtle shifts in light and the long-term gravitational evolution could ripple through ecosystems in ways we'd notice only after years of study. In the end, the moon's current locked stare is more than an astronomical curiosity. It's a kind of cosmic metronome. It gives us predictability, a surface we can point to and say, "That's home." It gives the night a steady face, an anchor for stories and science alike. Losing that would not mean losing the moon. It would mean losing a companion in a different way. One that spins, reveals new secrets, and refuses to stay the same. For some of us, that would be a loss of comfort. For others, it would be an invitation to rediscover the night every single evening. Either way, it's hard not to feel a little protective of the moon's quiet constancy. The way it rises, sets, and returns with the same calm expression, like a friend who never changes their mind about greeting you. Chapter 10. The Slow Drift Away. And yet the moon we stole a look at a moment ago is not frozen in place. It's drifting away, slowly, almost imperceptibly, like a friend stepping back at a long and gentle farewell. Scientists measure that step as about 3.8 centimeters a year. That's less than the length of your little finger, but over time it adds up. How do we know? Think of a lighthouse mirror and a very precise stopwatch. During the Apollo missions, and even earlier with Soviet probes, astronauts and engineers left small mirrors, retroreflectors, on the lunar surface. Today, teams on Earth fire laser pulses at those mirrors and time how long the light takes to return. From that timing, with astonishing precision, we can calculate the exact distance to the moon. The result? The moon is steadily, measurably moving outward. Why does this happen? The answer lives in the tides and in a basic rule of physics. Angular momentum is conserved. Earth spins. The moon orbits. Earth's gravity tugs on the moon, and the moon tugs back. Not just on the oceans, but on the entire planet. The tidal bulge that Earth's oceans form isn't perfectly aligned with the line between Earth and moon. Because Earth rotates faster than the moon orbits, those bulges sit slightly ahead of the moon, and gravity between the bulge and the moon acts like an ever so slight forward push on the moon. That push adds a tiny bit of energy to the moon's orbit, boosting it outward. The energy doesn't come from nowhere. It comes from Earth's rotation. So as the moon gains orbital energy and drifts away, Earth loses some rotational energy and slows. Our days lengthen, imperceptible on a daily basis, but real over long stretches of time. Imagine a figure skater spinning with arms tucked in. If she slowly extends her arms, she spins more slowly. Now picture that angular momentum being transferred to a partner. The skater points a foot outward and the partner drifts further away. The principle is similar. A small transfer, repeated endlessly, leads to a measurable change. You'll often hear the number 3.8 centimeters and think, that's nothing. Context helps. The average distance to the moon is about 384,000 kilometers. So 3.8 centimeters is indeed tiny by comparison. A hair on the scale of the whole system. But this is a process that's been working for billions of years. Small increments accumulate into profound shifts. Billions of years ago, the moon was much closer. Earth's spins were faster and days were shorter. In a far future that we can only imagine, so distant it's almost a story, days on Earth will be longer, and the moon will sit a little farther out, still presenting that same familiar face, because its rotation is already locked to its orbit. That same face, the ancient face of the moon, is a comforting constant. The moon is tidally locked. It rotates on its axis in the same time it takes to orbit Earth. So from here, we always see the same hemisphere. Even as the distance changes, that lock remains. So tonight, or 1,000 nights from now, the crescent, or the full circle, is still the crescent, or the full circle, the Maria and the Highlands in familiar arrangement. Change and continuity at once. What does this mean for us, living our lives measured in years and decades? For the most part, practically nothing. The change is so gradual that human lifetimes, even the longest family histories, barely notice. But there are ways we feel the echo of that process. Tides themselves, which are driven by the moon's pull, shape coastlines, nourish ecosystems, and have long guided human activity. Fishing, shipping, stories. The mechanism that inches the moon outward is the same one that lifts and lowers our seashores twice a day. It's a beautiful reminder that processes operating on very different timescales, the daily rhythm of tides and the billion-year drift of orbits, are facets of the same celestial choreography. There's also a poetic lesson here about balance and change. People often imagine equilibrium as a fixed state, a perfect stillness. But in nature, balance is often dynamic. The Earth-Moon system is a ballet of give and take, energy sliding from one partner to the other. creating a new configuration that still counts as balance. The moon being farther away isn't chaos, it's a new kind of order. And for the science-minded among you, this slow drift provides a kind of cosmic clock. By studying the moon's recession and geological evidence preserved on Earth, growth rings, sediment layers, tidal rhythmites, scientists can rewind parts of Earth's history and learn how fast days spun when life was young. It ties celestial mechanics to biology and geology, linking the spin of our planet to the growth of ancient corals and the rhythms encoded in stone. You might wonder, will this process ever stop? In theory, if nothing else intervened, Earth's rotation could slow enough that one day would equal one moon orbit. Earth and moon would be mutually tidally locked, turning the same face to one another. But the cosmos is messier than idealized math. The sun is aging. In a few billion years, it'll swell and reshape the inner solar system long before such a complete standoff is achieved. Still, the end point isn't the point here. The point is the ongoing gentle change, the slow drift that quietly reshapes our planet's rhythm, imperceptible in a lifetime, but steady across eons. It's worth making this personal. Think about the people and places you know that have changed with similar slowness. An old tree that's grown wider each year, a coastline that has crept up the beach over generations, a neighborhood that's shifted one block at a time. Those are human-scale versions of the same idea, small increments, nearly invisible in the moment, adding up to transformation. Standing under the moon's cool light, it's humbling and oddly comforting to know that the same process governs both the turning of our days and the widening of our world. So when you next look up at that familiar face of the moon, remember that it's both a constant and a traveler. It's an anchor for tides and stories, a marker of night, and at the same time a body that, with microscopic persistence, moves away. The balance between Earth and Moon is not a fixed statute, but a conversation, a tug here, a transfer there, that has been going on for billions of years and will continue, gently and inevitably. Let's carry that thought forward. This slow cosmic drift is one thread in a much larger tapestry of change. As we move on, we'll see how other forces, the tilt of Earth's axis, gravitational tugs from other planets, and the slow burn of the sun, weave together to shape the long-term story of our planet and its companion. Chapter 11. The Tides Between Us. You only have to stand on a shoreline once to feel the moon's quiet signature. Look out over water, and you'll see what looks like simple motion. A wave crawling in, then retreating. But that rhythm is actually a conversation between two bodies in space. Every tide on Earth is a silent echo of this cosmic relationship. The oceans rise and fall because the moon tugs at the planet, and that tugging is slow, sure, and utterly relentless. It's a kind of breathing, inhaling and exhaling coastlines, ecosystems, and even human lives. Think about the last time you were at the beach at different hours. Sometimes the sand is a narrow strip. Sometimes the shore stretches out for yards, and tide pools glimmer in the exposed rocks. That difference isn't random. It's the moon at work. As Earth spins beneath the moon's gravitational field, water is pulled into two bulges, one on the side facing the moon, where gravity is strongest, and one on the opposite side, where centrifugal forces created by Earth's rotation dominate. As your local coastline moves through those bulges, the sea level rises and falls, usually twice a day. That steady push and pull gives us the familiar pattern of high and low tides. It helps to picture the moon as a patient drum major, quiet, steady, yet orchestrating enormous motion. From our vantage point, the moon doesn't appear to change its face. It's tidally locked, showing us the same side. But that stillness is paradoxically the source of motion. Because it maintains a consistent relationship with Earth, its gravitational influence is regular. That regularity is what allows entire cultures to base calendars, rituals, and livelihoods on lunar cycles. Long before clocks and smartphones, people watched the moon and timed their lives to its phases. A full cycle from new moon to new moon, the synodic month, is about 29.5 days. Ancient farmers learned that certain phases were better for sowing or harvesting. Fishermen learned when the water would surge into estuaries and when flats would lie exposed. Mariners learned when channels would be deepest. If you've ever planned a beach picnic or a tide-pooling afternoon, you're doing the same kind of thinking, even if you check an app rather than the sky. There's also a seasonal heartbeat layered onto the daily rhythm. When the sun and moon line up, at new and full moons, their gravitational effects add together, producing spring tides, when highs are higher and lows lower. Roughly a week later, when they're at right angles, neap tides arrive. The differences are milder. These interactions between sun and moon made ancient timekeeping more complex and more precise. Calendars, based solely on the moon, drifted relative to the solar year. So many cultures adopted lunisolar calendars or added leap months to keep harvests aligned with the seasons. The point is that the moon didn't just mark nights, it helped organize years. The fingerprints of tides are visible in geography. Look at estuaries and salt marshes, mangrove stands at tropical coasts, the rias and fjords carved over millennia. In places like the Bay of Fundy, the tidal range is so extreme that vast stretches of seafloor are alternately drowned and exposed every day. Those dramatic contrasts created niches where specialized life thrives. Crabs that time their molts to the tides, birds that feed on exposed shellfish at low tide, seagrasses that can tolerate both freshened floodwaters and drying out. Intertidal zones are laboratories of adaptability, shaped by a rhythm that's both predictable and unforgiving. On a personal level, tides are also where many of us have our earliest memories of the ocean. I remember creeping across wet sand at low tide as a kid, peering into shallow pools and finding tiny, perfect ecosystems. Anemones waving, tiny crabs scurrying, a starfish clinging to a rock like a small piece of another world. Parents taught us to watch the horizon if we were out on a rock shelf. Get too engrossed in collecting shells and the water can creep up faster than you expect. Those small moments taught respect for the sea's timing. The moon's pull isn't dramatic in a single instant, but it has the power to change the entire landscape by the hour. People who make their living on the water are particularly intimate with this rhythm. Fisherfolk read tidal charts like a second language. For oyster farmers, the difference between a thriving bed and a failed season can hinge on knowing precisely when the water will flush nutrients and larvae in and out. Ports are built with tides in mind, dredging schedules adjusted around expected highs and lows. Even the medieval tidal mills that dotted European rivers used the rise and fall of water to grind grain. Humanity harnessing lunar motion in the most practical of ways. And now, in an age of engineers and turbines, we're looking at tides again as a source of energy. Tidal power is appealing because it's predictable. The moon gives us a timetable you can set your watch by. Where currents and tidal ranges are strong, turbines can convert that reliable motion into electricity. It's a reminder that the moon's influence is not just poetic, it's actionable. Culturally, the tide-moon relationship has a deep emotional resonance. Entire festivals and religious observances orbit lunar calendars. Communities historically timed feasts, fasts, and pilgrimages to the moon's phases, because those phases governed food availability and safe travel. Even our language holds traces of that link. The word month comes from the same root as moon. In literature and folklore, the moon and tides become metaphors for longing, for the push and pull of relationships, for cycles we can't escape. There's also a long-term thread to this story. Tides have shaped Earth's rotation itself. Over geological time, the moon's pull has acted as a brake on Earth's spin, lengthening our days. In a way, the moon helped set the tempo of life on the planet, not just the hours of a human day, but the evolutionary context for rhythms in behavior and development. So when you next stand on a shore and watch water creep in, listen for that hidden conversation. The moon may look like a still, distant coin in the sky, but its influence is a living force that sculpts coastlines, times migrations, feeds cultures, and powers machines. It's intimate and immense at once, a quiet partner that choreographs a ceaseless motion beneath our feet. That tidal breathing, the moon's invisible hand guiding the sea, connects moments as small as a child's first tide pool and as vast as the shaping of continents. It's a reminder that even the quietest presences in our sky can be the ones doing the most work, and that our everyday rhythms, from markets to meals, are often synced to this ancient lunar clock. Chapter 12. A Quiet Forever. There's a kind of hush that falls over everything when you look up at the moon on a clear night. Maybe you're alone on a porch. Maybe you're lying on your back in a field. Or maybe you're walking home with the soft glow above you. That face of the moon, the one we know so well, hasn't been changing for a very long time. It's not because the moon is frozen in place like a statue. It's because over eons, it found a rhythm with Earth and settled into a quiet, shared motion. Think of two dancers slowly circling each other. At first they're stumbling, tugging, each with their own spin. But over time their steps synchronize until every turn and pivot matches the others. That's what happened with Earth and the moon. Long ago, the moon spun faster relative to its orbit. The tides Earth raised on the moon's molten or semi-molten body acted like subtle brakes. Those tides took energy out of the moon's rotation, and bit by bit synced its spin to its orbit. Now the same side always faces us. It's not stuck, it's flowing, locked in a gentle gravitational choreography. There's something strangely comforting about that permanence. When you were a child, maybe you traced the bright seas and dark highlands of the moon with a finger in a picture book. Maybe an older family member pointed out familiar shapes. A rabbit, a face, a canoe. Shapes that people around the world have seen in the moon for generations. The person who looked up with you decades ago, and the person who will stare at that same patch of light a century from now, will see the same face. That continuity connects us in a way that feels almost sacred, a single, changing species, watching a steady companion night after night. Scientifically, the idea is called tidal locking, but you don't need the term to feel the effect. Imagine the mild tug of tides at the ocean, the way the water bulges toward the moon and then recedes. Those tiny movements transfer energy. Over unimaginable spans of time, those tiny influences add up and transform motion. The moon's rotation slowed until it matched the period of its orbit, and now rotation and orbit are simply different words for the same motion seen from different perspectives. Its efficiency and inevitability made graceful. That makes the moon a kind of cosmic promise. In a sky full of transient flares and exploding stars, there's one luminous presence that offers continuity. On restless nights, when life feels like it's shifting too fast, jobs, cities, relationships, the always-on scroll of news, the moon's steady face can feel like a refuge. It's not indifferent to change. It has been shaped by time and force. But its steadiness proves something subtle. Not all motion must be frantic to matter. Stillness can be its own kind of motion. There's also a humility to it. The moon didn't win anything by stopping its spin. It simply found balance. Earth and moon exchanged energy and settled into a state neither could forcefully claim as a victory. If you think about your own life, there are moments when you resist the current and moments when you let yourself move with it. Sometimes letting go feels like loss, but like the moon, you might find that flowing with what's around you leads to a quieter, more lasting harmony. Picture someone you love now, someone who taught you to look up, or someone you used to look up beside. Imagine them many, many years ago, their chin tilted back, their eyes catching that same crescent or that same scarred face. The same human faces, different generations, all linked by one constant light. It's an oddly intimate thought, a loop of people all peering at the same silent witness. So tonight, when you turn your gaze upward, try this. Breathe in slowly, and let the rhythm of your breath match the idea of a motion that's also stillness. Know that what you're seeing is the result of patient forces played out over billions of heartbeats of the planet. In the end, the moon doesn't resist Earth's gravity. It flows with it. Its spin and orbit are no longer separate, but one. The same face we see tonight is the same one humans have looked upon for tens of thousands of years. It's a constant in a universe full of change. As you close your eyes, picture that steady light above, locked in harmony, whispering across space. Stillness can be its own kind of motion.